Hi, my name is Antonio Font, and today I will make a brief yet educational video about sound in music instruments, in order for the viewers to understand more about this fun topic. Music plays a very big part in our life, whether you listen to it or practice playing an instrument. So, what is music? How does it work? And what is the physics behind all this? Sound is a longitudinal wave, meaning that the medium that the wave travels through oscillates, or moves back and forth in the same direction the wave is moving. These waves are similar to the ones on a slinky. In order to understand this concept, we need to know some definitions first. A longitudinal wave is a wave that oscillates back and forth on an axis that is the same as the axis along which the wave grows. A medium is a substance that carries a wave from one location to another. And finally, an oscillation can be a periodic motion that repeats itself in a regular cycle. Longitudinal waves have compressions and rarefactions. A compression is a region in the wave where the particles are closest together. A rarefaction is a region in the wave where the particles are farthest apart. The slinky is a perfect example, as you can see the rarefactions at the top and the compressions at the bottom. Strings, bass, and wind instruments use the standing wave. It looks like a wave that isn't moving, however, it doesn't travel anywhere, but its amplitude may change. The amplitude of a wave is the size of the vibration, and this determines how loud the sound is. We have learned that the larger the vibration, the louder the sound is, and vice versa. Frequency is the speed of the vibration, and this determines the pitch of the sound. It is only meaningful for musical sounds. Frequency is measured as the number of wave cycles that occur in 1 second. The unit of frequency measurement is hertz. One wave means one wave cycle per second. The more hertz there are in a frequency, it means that the cycles are much shorter and closer together. The wave with 10 hertz matches this characteristic. A point of a standing wave that doesn't oscillate are called nodes, while the points of maximum height are called antinodes. The piano is the simplest way to understand a standing wave. For my first lab, I will show how many antinodes and nodes a piano normally has. In a piano, waves made by a fixed string will have at least 2 nodes. The most usual is for it to have just one antinode in the middle. It is like a one-dimensional jump rope. For my second lab, we know a string will usually vibrate at a number of different standing wave frequencies. All waves in a string travel with the same speed, so waves with different wavelengths have different frequencies. Higher frequency oscillations result in higher pitched tones, while lower frequency oscillations produce lower pitched tones. Here are some tunes to understand the frequency in instruments. Pitch is how high or low a tone sounds when you hear it. Based on this, we'll do the following analysis. After listening to these first two tunes, we notice that they have a higher pitch. Therefore, they have a higher frequency oscillation. The third tune has a lower pitch, so it has a lower frequency oscillation. For the math analysis, this is the formula I chose. The frequency of a standing wave with two fixed ends will be equal to the number of harmonic times the fundamental frequency. The fundamental is the first harmonic. It is the most basic kind of standing wave. It has the fewest notes and antipodes. An overtone adds to the fundamental, and each overtone adds a note and an antinode. The harmonics are the fundamental waves and overtones combined. The fundamental is the first harmonic and the overtones are higher number harmonics. This explains why musical instruments sound different even when they're playing the same note. To summarize the whole video, our new learnings consist of what is sound, what is a longitudinal wave, what is a standing wave, how frequencies affect standing waves, and therefore affect the pitch of the sound and its harmonics, or how pleasant it sounds. Even if you didn't think of it at first, I hope that with this video you learned how the sound of musical instruments are all related to these factors and science itself.